In the heart of the Amazonian jungle, an old man from an isolated tribe walks along the familiar paths of his village. Each tree, each animal, each sound of the forest is as familiar to him as the beating of his own heart. He moves with determination. His feet barely make a noise on the soft earth as he picks herbs. The jungle, with its imposing trees and vibrant fauna, is his entire world. He does not know any place beyond its leafy, exuberant canopy. One afternoon, while the tribe gathers around the fire to share stories and meals, a strange noise breaks the usual sounds of the forest. The old man looks up, confused. The sound gets louder, and soon the source of the disturbance becomes visible. A metal bird bigger than any creature of the jungle descends from the sky and lands in a nearby clearing, its wings motionless and its body shining under the setting sun. The tribe is scared and curious at the same time. They observe from the safety of the trees, whispering to each other. The old man, brave and wise, approaches the strange bird, his heart beating 1,000 miles per hour. He is greeted by beings different from all those he has seen before and who speak in an unknown language. They offer him gifts and try to communicate, but the old man's first instinct is to protect his people. He gestures for the tribe to retreat without losing sight of the newcomers. When the sun sets and the metal bird leaves, the old man stays on the edge of the clearing, watching the sky darken. He wonders about the world beyond the jungle. Where did these visitors come from? What lies beyond the vast canopy that he has always known? The universe, which before was limited to the edges of the forest, now seems smaller, and he wonders about other invisible worlds and wonders. The observable universe is an immense structure full of diverse celestial objects scattered through vast expanses so wide that even light gets lost traveling around it. The journey of a photon from the sun to our nearest neighboring star exceeds 4 light years and encompasses distances between galaxies, which takes millions of years. Realizing that these vast expanses are mere grains of sand in the cosmos fills us with awe. So, what really is the observable universe, and how far does it extend? Our solar system is just one among countless others scattered throughout our galaxy. It has the central star, the Sun, in its main sequence phase, orbited by 8 known planets and their moons. Beyond these larger bodies, the solar system houses millions of smaller celestial objects, such as asteroids, comets, and meteoroids. The Moon orbits Earth at a distance of about 384,000 kilometers, which light can travel in approximately 13 seconds. This proximity has made the Moon the only celestial body beyond Earth that human beings have visited. Traveling outward, we arrive at an inner planet, Mars. Mars orbits the Sun at an average distance of approximately 15 astronomical units. An astronomical unit is the average distance between Earth and the Sun, approximately 14,996 million kilometers or 93 million miles, which provides a useful scale to measure distances within our solar system. Beyond Mars is the asteroid belt, full of millions of rocky and metallic fragments that extend between 21 and 33 Australian dollars from the Sun. This region probably represents the remains of a protoplanet that could not form due to the immense gravity of Jupiter. Jupiter itself, the gas giant of our planetary neighborhood, orbits at about 52 Australian dollars. The enormous gravitational field of this gas giant has profoundly influenced the architecture of the solar system, including its collection of diverse moons, from the volcanic Io to the icy Europa, admired for its extensive ring system. Saturn orbits the Sun at about 95 Australian dollars. Beyond Saturn, the solar system extends towards the colder and darker realms of Uranus and Neptune, the farthest known planet, which orbits at about 30 astronomical units from the Sun, equivalent to 4 light hours. Surprisingly, Neptune's trajectory only covers a fraction of the immensity of our solar system. Neptune's orbit, although extensive, captures only a fraction of our solar system. Beyond Neptune extends the Kuiper Belt, where dwarf planets like Pluto reside. At about 39 Australian dollars from the Sun, the most distant object that we have discovered so far located at about 132 astronomical units, which translates into 18 light hours. But even this distant object is not even close to the outer edge of the supposed ancient cloud that is believed to extend up to 100,000 astronomical units from our Sun, marking the limit of the gravitational influence of our solar system and the beginning of interstellar space. This limit marks the end of the gravitational influence of our Sun and the beginning of interstellar space. Now, traveling further away from our solar system, we have empty space and space clouds. However, much further beyond that, our cosmic neighborhood is rich in a variety of stars ranging from the closest to the Sun to those on the outer edge of our immediate stellar community. In a space of only about 20 light years, more than 50 stars offer a glimpse of the universe that surrounds us. Our first stop is Proxima Centauri, located about 424 light years away. This red dwarf star is orbited by at least 2 planets, one of which, Proxima b, is within the star's habitable zone. This rock is where conditions could be adequate for liquid water to exist on the surface, which raises the possibility of life beyond Earth. A little further from Proxima Centauri are Alpha Centauri A and B, which shine intensely at about 437 light-years away from us. These 2 stars form a binary system, with Alpha Centauri as similar to our Sun and Alpha Centauri b, slightly smaller and colder. The dynamics of this binary system provide crucial information about how planetary systems can form and evolve around similar binary pairs. Beyond the Alpha Centauri system, we find the Starbad star, a red dwarf about 6 light-years away, known for its rapid movement through the sky and which stands out for its age and activity. Although it was initially expected to host exoplanets, researchers have come to the conclusion that there are no planets. Another notable neighbor is Wolf 359, about 78 light-years away. This red dwarf is one of the faintest and least massive stars observed so far. It is a flare star, meaning it suffers sudden increases in brightness due to magnetic activity. We cannot talk about nearby stars without mentioning Sirius, the brightest star in our night sky, around 86 light-years away. Sirius is a binary stellar system formed by a main sequence star, Sirius A, and a faint white dwarf, Sirius B. The system is especially important for studying the atmospheres of white dwarfs and stellar evolution. About 11 light-years away, Ross 128, a red dwarf, houses an exoplanet the size of the Earth, Ross 128 bits, which is a priority target for studying planetary atmospheres and conditions that could harbor life. Located about 122 light-years away is an interesting case. It is an old red dwarf with minimal stellar activity, but it houses at least 2 terrestrial planets. Its proximity and the characteristics of its planets make it an excellent target for direct imaging and atmospheric study in the future. Another notable mention is that of Vo-Z-Keti, a star located about 12 light-years away and known for its multiple Earth-sized planets. What makes this system unique is the compact arrangement of its planets, challenging our models of how planetary systems develop. Located about 125 light-years away, this star was discovered in 2003 due to its very low brightness. It has at least 2 Earth-like planets, both potentially within the habitable zone. This stellar system raises interesting questions about the longevity and stability of habitable conditions. Our journey would not be complete without visiting one of the most distant neighboring stars, about 20 light-years away. G832, located about 16 light-years away, this red dwarf star houses a planet that has aroused great interest, G832c. Now, if we talk about our galaxy, the Milky Way, it is a vast and complex structure full of wonders and mysteries. At the heart of this immense galaxy is our solar system, located in the Orion Arm, one of the spiral arms of the galaxy. These arms, full of stars, dust, and gas, extend outwards from the central bulge, creating the beautiful spiral pattern characteristic of many galaxies like ours. The Milky Way houses approximately 400 billion stars, each with its own history and possible planetary systems. Among these stars, scientists estimate that there could be more than 1 trillion exoplanets orbiting stars other than our Sun. The diameter of the galaxy is estimated to be about 100,000 light-years, which means that light traveling at 300,000 kilometers per second would take 100,000 years to cross the galaxy from one side to the other. The Milky Way is a barred spiral galaxy, which means that it has a central bar-shaped structure composed of stars. Surrounding the main disk of the Milky Way is a stellar halo that extends even further and may be twice the diameter of the main disk. The thickness of the main disk of the Milky Way is about 1,000 light-years. However, in the center of the galaxy, there is a bulge where the density of stars increases dramatically. This central bulge, about 3,000 light-years thick, contains a dense concentration of stars, gas, and potentially a supermassive black hole known as Sirius A. Within the Milky Way, our solar system is located about 27,000 light-years from the galactic center, nestled in the Orion Arm. This arm is a minor spiral arm located between the larger arms of Sagittarius and Perseus. The Orion Arm houses many known stars and constellations visible from Earth, including the famous constellation Orion. Beyond our immediate stellar neighborhood, the Milky Way is full of a myriad of celestial objects and phenomena. There are massive star formation regions, such as the Orion Nebula, where new stars are born from clouds of gas and dust. There are also ancient star clusters, some of which are almost as old as the galaxy itself, which provide valuable clues about the early stages of the formation of the Milky Way. When we look beyond our immediate galactic neighborhood, we discover that the Milky Way and its companions in the local group are part of a much larger structure known as the Virgo supercluster. This supercluster is a huge collection of galaxies that allows us to glimpse the immensity of the universe. First is the Virgo supercluster, which houses more than 30,000 galaxies and extends over an immense area of space with a diameter of about 150 million light-years, making it one of the largest known structures in the universe. The combined mass of all the galaxies in the Virgo supercluster is estimated to be around 1 quadrillion solar masses. To put it in perspective, this is roughly equivalent to the mass of 1,000 Milky Way galaxies. The Virgo supercluster is not a spherical object, but is quite bulky, with approximately 60% of its galaxies forming a flat sheet about 10 million light-years thick. This flat structure is due to the gravitational forces that have shaped the distribution of galaxies over billions of years. The Virgo supercluster is part of an even larger structure known as the Laniakea supercluster, which means immense sky in Hawaiian, encompassing several superclusters, including the Vivio supercluster and the Great Attractor. The Laniakea supercluster extends approximately 520 million light-years, making it one of the largest known cosmic structures. The total mass of the Laniakea supercluster is estimated to be around 100 quadrillion solar masses. This enormous massive formation not only contains our own galaxy and its neighbors, but thousands of other galaxies, each with its own unique properties and potential to harbor life. At the heart of the Laniakea supercluster is a region known as the Great Attractor, located approximately 250 million light-years from Earth. The Great Attractor acts as one, attracting galaxies toward it. This region exerts a significant gravitational attraction on the galaxies of the supercluster, including our own Milky Way. The Great Attractor cannot be observed directly from Earth because the plane of the Milky Way prevents us from seeing it. This has made studying the Great Attractor a difficult task for astronomers. Despite this difficulty, scientists have deduced its existence through the movement of galaxies that appear to be attracted to this mysterious region. The exact nature of the Great Attractor remains an enigma. It is believed to be a dense region of space with a huge concentration of galaxies and dark matter. This concentration of mass exerts a powerful gravitational pull that influences the movement of galaxies over great distances. As we continue to move away from the Lancer superstructure, we see it as part of a larger cosmic network. The cosmic web is a vast network of interconnected filaments, walls, and voids that make up the large-scale structure of the universe. These filaments are composed of galaxies and clusters of galaxies, extending over billions of light years. The cosmic network is shaped by the gravitational forces of dark matter and the universe's expansion. The galaxies and clusters form along these filaments, while huge voids are found between regions with relatively few galaxies. In addition, our observable universe extends billions of light years through not only the clusters of galaxies that we can detect, but also includes some objects that we have not yet discovered. The observable universe includes all the matter and energy that we can observe from Earth, limited by the speed of light and the age of the universe. Since the universe is about 138 billion years old, we can only see light that has traveled up to 138 billion years to reach us. However, due to the universe's expansion, the observable universe extends well beyond 138 billion light years. The radius of the observable universe is believed to be about 4,665 billion light years, which makes the diameter about 93 billion light years. To put this in perspective, light travels at an amazing speed of about 300,000 kilometers per second. But even at this incredible speed, it takes billions of years for light to traverse the observable universe. If you could travel at light speed, it would take 93 billion years to travel from one end of the observable universe to the other. Within this immense expanse, astronomers estimate there are around 2 trillion galaxies, each with billions of stars. If you counted each galaxy at a rate of 1 per second, it would take you more than 63,000 years to finish counting them all. Considering that each of these galaxies contains billions of stars, the total number of stars in the observable universe is mind-boggling, potentially around 200 sextillion. Despite the immense scale of the observable universe, this is only a fraction of the entire universe. The actual size of the entire universe is unknown and could be infinitely larger than the observable part. The expansion of the universe means that objects at the edge of the observable universe are moving away from us faster than the speed of light, making it impossible to observe anything beyond this horizon. One of the most significant observations of cosmology is the cosmic microwave background radiation. This faint glow of light visible in all directions is the remnant of the radiation from the Big Bang, dating back to about 380,000 years after the formation of the universe. The CMB provides a snapshot of the universe in its infancy and marks the time limit of the observable universe. The universe has been expanding since the Big Bang, and this expansion affects our observations. Galaxies move away from each other, and the space between them expands. This means that the observable universe is continuously growing as light from more distant regions has time to reach us. The discovery of dark energy, a mysterious force driving the accelerated expansion of the universe, adds another layer of complexity to our understanding. Dark energy constitutes approximately 68% of the universe's total energy content, causing the rate of expansion to increase over time. This accelerated expansion implies that distant galaxies will eventually move beyond our observational reach, making parts of the universe forever inaccessible within it. Scientists believe that there are approximately 2 trillion galaxies, each of which contains billions of stars. These galaxies have various shapes and sizes, from spiral galaxies like our Milky Way to elliptical and irregular formations. The large number of stars within these galaxies suggests there could be countless planetary systems, many of which may harbor conditions suitable for life. One of the most profound images captured by the Hubble Space Telescope is the Hubble Deep Field, showing a small region of the sky teeming with thousands of galaxies, each a huge collection of stars, planets, and potentially life. It is believed that there are about 10,000 galaxies in the image alone, including galaxies of various ages, sizes, shapes, and colors. This image represents only a small fraction of the sky, highlighting the large number of galaxies that populate the observable universe. The detection of gravitational waves has opened a new era in astronomy. These waves in space-time, caused by violent cosmics, such as the fusion of black holes, provide information about phenomena that would otherwise be invisible to traditional telescopes. Gravitational wave observatories allow us to explore the universe in previously unimaginable ways. The observable universe encompasses not only vast distances, but also immense spans of time. When we observe distant galaxies, we are looking back in time, seeing them as they were billions of years ago. This is because it takes time for light to travel from those distant objects to us. The observable universe acts as a time machine, allowing us to study the history and evolution of the cosmos. Some of the most distant galaxies we observe today existed when the universe was only a few 100 million years old, providing information about the early stages of galaxy formation. But after all this, do you wonder how the universe has reached this point where we cannot find its limits, which extend billions of light years? To truly answer the question, we have to go back to the universe's birth. The answer may be found music there. One of the most interesting questions in cosmology is how the universe began. One of the main theories in modern cosmology is the Big Bang theory, which explains how our universe began and evolved. Imagine all the stars, planets, and galaxies compressed into an incredibly hot and dense point. Scientists believe that this is how it all began about 138 billion years ago. From this small, dense point, the universe began to expand and cool. This event, known as the Big Bang, marked the beginning of the universe's growth and the vast distances we observe today. The term Big Bang can be misleading, as it suggests an explosion occurring in space itself. However, the Big Bang was not an explosion in space, but rather an expansion of space itself in the first fractions of a second after the Big Bang. The universe expanded exponentially during a period known as cosmic inflation. During this brief period, the universe grew from an almost infinitely small point to macroscopic scale. As the universe expanded, it cooled, which allowed energy to transform into particles of matter. These particles combined, forming simple elements such as hydrogen and helium. For billions of years, these elements merged under gravity to form stars, galaxies, and planets. The formation of these elements occurred in the first minutes after the Big Bang, as the universe cooled enough for protons and neutrons to form nuclei. The Big Bang theory is supported by significant evidence. A key piece is the cosmic microwave background radiation, a residual glow from the early universe. This radiation provides a snapshot of a universe only 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that light could not freely travel. The uniformity and slight fluctuations in the CMB support the idea of cosmic inflation and the rapid expansion of the universe. Another piece of evidence is the redshift of galaxies. This redshift indicates that galaxies are moving away from us, demonstrating that the universe is expanding. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to move away from us, which supports the idea that the universe was once much smaller, hotter, and denser. While the Big Bang theory explains the expansion and evolution of the universe, it also raises questions. For example, it does not explain what lies beyond the observable universe. The theory of cosmic inflation suggests a rapid expansion immediately after the Big Bang, but leaves unanswered questions about the nature of the universe beyond what we could observe before the discovery of cosmic microwave background radiation. A rival theory, known as the steady-state theory, suggested that the universe had no beginning or end, but remained the same as a whole despite its expansion through the constant creation of matter. This theory was popular in the 1940s, but lost support after the discovery of the CMB in 1965, which strongly supports the Big Bang. Other theories, such as the cyclic model, suggest that the universe experiences infinite cycles of expansion and contraction. After the Big Bang, the universe initially expanded and cooled. It was a hot, dense soup of particles that, as it expanded, cooled and allowed the particles to come together to form the first atoms. These atoms came together to form the first stars and galaxies. The expansion of the universe continues today, with galaxies moving away from us in all directions. To think even further back, the first long-lived particles, the protons and neutrons that make up the atomic nucleus, appeared about 1,000th of a second after the Big Bang. Before that, matter as we know it did not exist. Physics allows us to go back even further in time to processes that took place before stable matter existed. The observable universe includes all the matter and energy that we can observe from Earth, limited by the speed of light and the age of the universe. Since the universe is about 138 billion years old, we can only see the light that has traveled up to 138 billion years to reach us. However, due to the expansion of the universe, the observable universe extends far beyond 138 billion light years. One of the key concepts for understanding this process is the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be known with arbitrary precision. This principle allows the temporary creation of particles from the vacuum, as long as they disappear quickly enough to comply with the law of conservation of energy. Quantum fluctuations can cause particles to appear and disappear shortly after. This may sound strange, but such particles have been observed in many experiments. The vacuum of space is full of particles that are constantly created and destroyed, apparently out of nowhere. This suggests that the quantum vacuum is actually something rather than nothing. Where did space-time itself come from? To answer this, we have to go back to the beginning, to the Planck era. This period was so early in the history of the universe that our best theories of physics no longer work. It occurred only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually, physicists use quantum mechanics for tiny particles and general relativity for large cosmic scales. But to understand the Planck era, we need a complete theory of quantum gravity that combines both. We still do not have a perfect theory of quantum gravity, but there are ideas such as string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper, microscopic processes. What we experience as space and time is the result of quantum processes that are difficult for us to understand because we're used to the large scale. Quantum fluctuations occur constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a brief moment, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone do not explain the vast scale and complexity of the universe. Dark energy exists, a mysterious force that fills all space and accelerates the expansion of the universe. Although we do not fully understand dark energy, it is believed to play a key role in the creation and evolution of the cosmos. So, how do we go from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, laying the foundation for the formation of galaxies, stars, and planets. Little by little, due to dark energy, these celestial objects began to push each other instead of attracting each other, leading the universe to exponential expansion. Dark energy is a mysterious force that counteracts gravity and causes the universe to expand at an accelerated rate. This accelerated expansion means that galaxies are not only moving away from each other, but are doing so at ever-increasing speeds. Over time, this could lead to a future in which galaxies move so far from each other that they become isolated, turning the universe into a much lonelier place. In conclusion, the birth and expansion of the universe involve complex processes governed by quantum mechanics and cosmic forces, such as the dark energy of the Big Bang and cosmic inflation, to the ongoing expansion driven by dark energy. These phenomena have shaped the observable universe that we see today. As our understanding of these processes grows, we continue to discover the profound mysteries of the cosmos and our place in it. The radius of the observable universe is believed to be about 465 billion light-years, making the diameter about 93 billion light-years. Despite the immense scale of the observable universe, this is only a fraction of the entire universe. The actual size of the entire universe is unknown and could be infinitely larger than the observable part. The expansion of the universe means that objects located at the edge of the observable universe are moving away from us at a speed greater than that of light, making it impossible to observe anything beyond this horizon. The universe has been expanding since the Big Bang, and this expansion affects our observations. Galaxies are moving away from each other, and the space between them is stretching. This means that the observable universe is continuously growing as light from more distant regions. Far regions has time to reach us within the observable universe. Scientists believe that there are approximately 2 trillion galaxies, each with billions of stars. These galaxies come in various shapes and sizes, from spiral galaxies, such as our Milky Way, to elliptical galaxies and irregular formations. The large number of stars within these galaxies suggests that there could be countless planetary systems, many of which could harbor conditions suitable for life. One of the most profound images captured by the Hubble Space Telescope is the Hubble Deep Field, which shows a small region of the sky teeming with thousands of galaxies, each a vast collection of stars, planets, and potentially life. This image represents only a small fraction of the sky, highlighting the large number of galaxies that populate the observable universe. To understand how the universe could begin from nothing, we need to explore the strange world of quantum mechanics in the realm of quantum physics. Nothing is not the absence of something, but rather a state of empty energy in which particles constantly appear and disappear. This phenomenon is known as quantum fluctuations. Quantum fluctuations occur in what is known as a quantum vacuum, a state with the lowest possible energy in which particles can momentarily appear and then disappear according to the laws of quantum mechanics. It is possible that these fluctuations lead to the creation of a universe. In this context, nothing is an energetic state that can give rise to matter and energy. But after understanding how our universe began, we also need to understand how it reached its current state. Cosmic inflation refers to a very brief period just after the Big Bang, when the universe expanded at an incredibly rapid rate. Imagine the universe as a tiny, very compact point that suddenly stretches and grows at an unimaginable rate. This rapid expansion occurred in less than a fraction of a second, making the universe much larger almost instantaneously. Scientists believe that this rapid expansion was driven by a special type of energy present in the primitive universe. This energy, often referred to as inflationary energy, caused space itself to stretch faster than the speed of light. Think of it as inflating a balloon in an instant, causing it to expand from the size of a pinhead to the size of a basketball. Before inflation, the universe was a chaos with random fluctuations in density and temperature. The rapid expansion spread everything evenly, creating a smooth and uniform universe on a large scale. Although inflation smoothed the universe, it also left small irregularities or fluctuations. These small differences in density grew over time under the influence of gravity, forming the galaxies, stars, and planets we see today. One of the most important tests of inflation is the cosmic microwave background radiation. The CMB is the faint glow of the Big Bang and provides a snapshot of the universe when it was only 380,000 years old. The uniformity of the CMB, with its slight temperature fluctuations, matches the predictions of inflation theory. The distribution of galaxies and clusters of galaxies in the universe also supports the idea of inflation. The way in which these structures are distributed and their size scales are consistent with the small fluctuations left by inflation. The universe appears to be geometrically flat, meaning that its shape follows the rules of Euclidean geometry. Inflation explains why the universe is flat, since rapid expansion would have smoothed out any initial curvature. Inflation solves the horizon problem, which asks why different parts of the universe so far apart have the same temperature and properties. The rapid expansion during inflation would have allowed these regions to be in contact with each other before inflation separated them. Inflation is driven by a hypothetical field called the inflaton field. This field, associated with a particle called an inflaton, had a very high energy density that caused the rapid expansion as the universe expanded. The energy of the inflationary fields decreased, which eventually led to the end of the inflation period. The energy of the inflat field then became particles and radiation that heated the universe and led to Big Bang nucleosynthesis, where the first elements formed during inflation. The tiny quantum fluctuations in the inflat field stretched to macroscopic scales. These fluctuations created slight overdensities and underdensities in the early universe. Over time, gravity amplified these fluctuations, leading to the formation of large-scale structures, such as galaxies and clusters. This helps to understand several key aspects of the universe, including why it looks the same in all directions and why the cosmic microwave background radiation is so uniform. It also explains the flat geometry of the universe observed in the CMB and provides a mechanism for the formation of galaxies and large-scale structures from initial small fluctuations. The theory of inflation not only suggests the expansion of the universe, but there is also an expanded concept of the theory known as chaotic inflation, which explains how the early universe may have experienced a period of rapid expansion. To understand chaotic inflation, let's start with a simple example. Imagine you have a magic balloon that starts out very small, almost too small to even see. Suddenly, this balloon begins to inflate at an incredibly rapid rate, much faster than any normal balloon you have ever seen. As it expands, some parts of the balloon get bigger, while others stop growing and remain the same size. This magic balloon is similar to a special part of space that experiences what we call chaotic inflation. In this theory, the universe is like a magic balloon. Some regions of space experience rapid expansion, growing exponentially, while other regions stay static. This gives rise to a patchy universe where different areas expand at different speeds. This irregular pattern means that the universe did not need a perfectly uniform starting point to begin its rapid expansion, but could have started expanding from almost any initial condition, whether smooth, irregular, or in between. Chaotic inflation explains that the expansion of the universe can begin in a wide variety of conditions, unlike the standard theory of inflation, which requires specific initial states. Chaotic inflation suggests that almost any type of space can suddenly begin to expand rapidly. This is due to the presence of a special type of energy field known as the inflationary field. The inflationary field can cause different regions of space to expand at different rates. In some areas, the energy of the inflationary field is high, leading to rapid expansion. In other areas, the energy is lower, resulting in slower expansion or no expansion. The regions that expand rapidly dominate, creating a universe that grows exponentially in certain areas, while remaining static elsewhere. To visualize chaotic inflation, imagine the universe as a landscape of hills and valleys. The inflatable field represents this landscape, where the height of the hills and valleys corresponds to the energy level of that field. In some regions, the field has high energy, causing rapid expansion. In other regions, the energy is lower, leading to slower expansion or no expansion. As time progresses, the regions at the top of the hills expand rapidly and dominate the landscape. These regions continue to grow, creating a universe that is both vast and varied. Chaotic inflation fits into the broader framework of the Big Bang theory by providing a mechanism for how different regions of the universe could have expanded rapidly after the initial explosion if it complements by suggesting that this rapid expansion could have occurred under a wide range of initial conditions, without requiring a perfectly uniform starting point. The universe resulting from chaotic inflation could be irregular, with some regions expanding faster than others. This irregularity can help explain the large-scale structure of the universe and the distribution of galaxies and clusters that we observe today. Chaotic inflation also introduces the possibility of multiple universes, or a multiverse, as different regions of space can expand at different speeds. It is conceivable that other universes with different properties may exist beyond our observable universe. So, according to this theory, the edge of the universe is not a single well-defined limit, but rather a mosaic of regions that have expanded at different speeds. Some areas may have stretched so much that they are beyond our current observational reach, creating a horizon that changes continuously as the universe expands. The idea of multiple regions that expand at different speeds also supports the possibility of a multiverse in which other universes with different physical laws could exist beyond what we can see. This makes the true edge of our universe not a clear limit, but a dynamic and constantly changing frontier. Music. To answer the question about the edge of the universe, it is necessary to understand the shape of the universe in general. For a long time, people thought that the universe was shaped like a sphere. This idea goes back to Aristoteles, who believed that the Earth was inside this sphere, separated from the rest of the universe by a boundary where space stops, similar to the edge of what we see. But explaining what happens at this limit is really difficult, even for the smartest people and the most advanced computers. It is difficult to describe what a universal limit would be like or how it might exist. We do not see any sign of such a barrier. There does not seem to be any place in space, except perhaps black holes, where light stops, so we now think that regardless of the size or shape of the universe, it probably does not have a physical edge like the one we can observe. Instead of everything being inside a sphere, it is more like we are on the surface of a sphere. The surface of a sphere is finite, but has no edges. Think of the Earth. Its size is limited, but you can fly around it forever without hitting any edge. You would never run out of Earth to fly over, because gravity would return you to your starting point. Similarly, it is believed that the gravity of the universe, like matter, causes the same effect. However, when we use mathematics to try to describe this limit, it becomes really complicated. Even the smartest people and the most powerful computers have difficulty explaining what a universal limit would be like or how it would exist. When we look into space, we do not see any indication of a limit. Light travels freely, except near black holes, where it is trapped. This means that the universe probably does not have a physical edge, but we think of the universe as the surface of a sphere. Think about the surface of the Earth. It is of limited size, but you can keep traveling around it without ever reaching an edge. Gravity simply returns you to your starting point. It is believed that the universe works in the same way. The gravity of all the matter in the universe curves space so that you could travel forever and never find an edge. The universe could be infinite, or it could wrap around itself like the surface of a sphere. This means that you could keep traveling in one direction and eventually end up where you started, just like on Earth, in perfect balance between the possibilities of a universe with positive or negative curvature. There is a scenario called critical density. In this case, omega is exactly 1, which means that there are approximately 57 hydrogen atoms per cubic meter of space. At this density, the effects of gravity and dark energy balance each other, resulting in no global curvature, making the universe flat. A flat universe without curvature cannot close on itself, and is the type of universe that we would expect to be truly infinite. In this universe, space behaves like an infinite flat sheet of paper. Two parallel light photons would remain parallel forever, traveling through an infinite space with gravity and dark energy in perfect balance. A flat universe is smooth and continues to expand without ever collapsing, even if it is on the verge of a collapse. This would only happen after an infinite amount of time. So, in reality, it will expand forever, like a universe with negative curvature. Scientists were very interested in finding out the shape of the universe. But how do you measure its curvature? There are two main methods. The first is to add up the total energy densities in the universe by observing its large-scale properties. The discovery of the almost uniform microwave sky in the 1960s suggested that the universe could be at critical density, and the discovery of cosmic acceleration in 1997 showed that space could have a negative curvature or be very close to being flat. The second, more accurate way to determine the shape of the universe is by studying the cosmic microwave background. This is the residual radiation from the Big Bang, which acts as a snapshot of the universe when it was only 379,000 years old. If there is any curvature in the universe, we are likely to find it here. The CMB has a very uniform appearance, equal in all directions, with only small temperature fluctuations. These fluctuations come from density differences in the early universe. Measuring the sizes and distances between these hot spots, scientists can look for distortions in the radiation. Then they draw triangles between these areas and measure the angles to determine the curvature of the universe. In a universe with positive curvature, the angles would add up to more than 180 degree. In a universe with negative curvature, they would add up to less than 180 degree. In a flat universe, the angles would add up to exactly 180 degrees. Using this method to map the CMB with its shape, concluding that omega is exactly 1 with a 10% margin of error, suggesting that the universe could be flat. Later, NASA's Wilkinson Microwave Anisotropy Probe provided even more accurate measurements that reaffirmed that the universe is largely flat and critically dense. In 2010, the European Space Agency's Planck satellite offered the most detailed dataset of the early universe, also concluding that the universe is very close to being flat. The question remains, why is the universe so perfectly designed or shaped? Even if the universe has a slight curvature, the fact that we cannot determine it after almost 14 billion years suggests that it was very close to being critical in the Big Bang. This perfect balance is known as the flatness problem, and understanding it is a key target in modern cosmology. There are 3 possible solutions to the flatness problem. The universe could be truly flat and infinite. It could be curved, but on such a large scale that we cannot detect it, or it could have a shape that hides its true dimensions from us. The idea of an infinite universe is profound, but difficult to imagine, especially considering that the Big Bang Theory suggests that our universe has properties that we would expect to see in an infinite universe, such as certain limits, for example. The Planck satellite discovered that the variability in the power spectrum of the CMB flattens significantly at scales larger than our observable universe, suggesting a limit that would not be expected in an infinite universe. It is possible that the universe has a shape that hides its true size from us, with a complex structure. In conclusion, although we have evidence that suggests that the universe is flat, the true shape of the universe remains one of the greatest mysteries of cosmology. As we search for the edge of the universe, we also need to understand the center of the universe. The universe is undeniably vast, and from our perspective, it may seem that Earth is at the center of everything. But is there an aroma of the cosmos? And if so, where is it? If the Big Bang started the universe, then where did everything come from, and where is it going? To begin to discuss these questions, let's go back about 100 years. In the 1920s, astronomer Edwin Hubble made 2 amazing consecutive discoveries. In the early decade, he discovered that the universes of Lambda, now known as galaxies, are very far from us. Later in that decade, he discovered that, on average, all the galaxies are moving away from us. There is already a useful theoretical explanation for this. Einstein's theory of general relativity had predicted that the universe was dynamic, either expanding or contracting. This differed from the prevailing view at the time, which held that the cosmos was perfectly static. A group of scientists working semi-independently took Einstein's equations seriously and developed a solution. This solution to Einstein's equation, along with Hubble's observations, tells us that we live in an expanding universe, that on average, all galaxies are moving away from each other, and that long ago, all the matter in the cosmos was compressed into an infinitely small point known as the Big Bang singularity. So where's the Big Bang? Surely, that would be the true center of the universe. Unfortunately, the reality that we have discovered about the universe through modern science does not lend itself to an easy explanation or even the ability to imagine it. That's because there is no center of the universe. There is no edge either. The cosmos is not expanding from anywhere and is not expanding to anywhere. In simpler terms, The Big Bang did not happen at a single point in space, but happened throughout the universe at once. Imagine the universe as an inflated balloon. Each point on the surface of the balloon moves away from all other points as it expands, but there is no center on the surface of the balloon. Similarly, our universe expands in all directions, but there is no central point from which everything began. In conclusion, although it may seem that there should be a center of the universe, the truth is that the universe has neither center nor edge. The Big Bang occurred everywhere, and the universe continues expanding uniformly in all directions. First, let's address the idea of an edge. The universe includes everything that exists. Edges divide one region from another, but since the universe includes all regions, it cannot have an edge. This means that the universe could be infinitely large, and it is impossible to point out the center of an infinite space. Another possibility is that the universe is finite, but at very large scales, far beyond what we can observe, the universe could curve on itself, which would mean that it still does not have a center. Think of it like the Earth. You can point out the center of the free space of the Earth, which is the molten core, but you cannot point out the center of the surface of the Earth. It could be any point on the surface because no point is more central than another. This means that the Big Bang occurred everywhere in the universe at the same time. It occurred in the room you're sitting in and in the farthest galaxy we can see. The Big Bang was not a single point in space. It was a moment in time. It is part of the past of everything in the universe. However, there's a twist. The universe is about 1,377 billion years old because light travels at a limited speed and we can only see a part of the universe. The limit of what we can see is about 45 billion light years away because the universe expands faster than light. Most of the universe is hidden from us, like the beam of a flashlight in a dark forest. We can only see up to the limits of light from our perspective. All other galaxies appear to move away from the Milky Way. It seems that we are in the center of the universe, but the same can be said of any galaxy from its perspective. They are in the center of their observable universe, and all galaxies move away from them. This is the nature of an expanding universe. There is no true center, but all observers, including us, can feel that we are in the middle of it. To understand why there is no center in the universe, imagine inflating a balloon. As it inflates, all the points on its surface move away from the others. There is no center on the surface. All points expand, moving away from each other equally. This is similar to how our universe expands. The Big Bang was not an explosion from a single point into empty space, but the rapid expansion of space itself that occurs everywhere at once. Now let's talk about the observable universe. Because light travels at a finite speed, we can only see the parts of the universe for which light has had time to reach us. This creates a spherical bubble around us called the observable universe, which measures approximately 45 billion light years in radius. This does not mean that the universe is only 45 billion light years wide. It only means that that is the limit of what we can see. Beyond that, the universe continues, but it is hidden from us due to the finite speed of light and the continuous expansion of space. Imagine you are in a huge and foggy field, and you can only see as far as the fog allows you. The edge of your vision is not the edge of the field, but the limit of what you can see. Similarly, the observable universe is only the part we can see. The actual size of the universe is much larger and possibly infinite. Because of this, each point in the universe looks like the center from its own perspective. If you were in a galaxy billions of light years away, you would see galaxies moving away from you, just as we see it from Earth. This uniform expansion makes it seem that each point is the center, but in reality, there is no central point in the context of the universe. Space itself is expanding uniformly, and each point moves away from all the others. This means that there is no single place that can be considered the center. So, does that also mean that, due to the expansion of space, we will not be able to discover the edge of the universe? Music. After talking about the center of the universe, we need to understand more about the edge of the universe. When we talk about the edge of the universe, it is essential to understand what we mean by edge in everyday terms. An edge is a limit where something ends, like the edge of a table or the edge of a sheet of paper. However, when we talk about the universe, the concept of an edge becomes much more complex and fascinating. The universe includes everything that exists, all space, time, matter, and energy. So, can such an omnipresent entity have an edge? First, let's consider the idea that the universe is infinite. An infinite universe would have no limits, which means that it would extend forever in all directions. In such a universe, it would be impossible to point out a center or an edge, because each point would simply be another point. This is similar to the surface of a balloon that expands as air is blown into it. As the balloon inflates, all the points on the surface move away from all the other points, but there is no edge on the surface itself. Each point on the balloon could be considered the center from its own perspective, but in reality, there is no central point. Now let's think about the observable universe. This is the part of the universe that we can see or detect. The observable universe is limited by the speed of light, which means that we can only see the light that has had time to travel to us from the beginning of the universe, about 138 billion years ago. This creates a spherical bubble around us with a radius of about 45 billion years called the cosmic horizon. Beyond this horizon, the light from the most distant parts of the universe has not had enough time to reach us, making those regions invisible to us. Music, the observable universe, can be compared to standing in a foggy field with a flashlight. The light from the flashlight only allows you to see a certain distance, and beyond that point, everything is hidden by the fog. This does not mean that the field ends where your light ends. It just means that you cannot see beyond that point. In the same way, the observable universe is limited by the distance that light has traveled, but the universe itself likely continues much further beyond what we can see. A common mistake is thinking that the edge of the observable universe is the edge of the real universe. In reality, the observable universe is only a small part of the entire universe, which could be far larger or even infinite. The microwave acts as a wall of light that marks the edge of our observable universe. Beyond this, we cannot see anything directly because the universe was opaque before that moment. To understand what could be beyond the observable universe, scientists rely on the principle of cosmological homogeneity, which states that the universe on a large scale is uniform and has the same appearance in all directions. This principle suggests that the regions beyond our observable universe are probably similar to what we see within it: galaxies, stars, and cosmic structures that extend into the unknown. If we could somehow see beyond the cosmic light horizon, we would probably find more of the same: a cosmic network of galaxies and voids. Music, to better illustrate this idea, let's imagine we travel to the edge of the observable universe. As we move outward, we would pass through billions of galaxies, each containing billions of stars and countless planets. These galaxies are organized into clusters and superclusters interconnected by vast filaments of dark matter and gas that form a complex cosmic network. Finally, we would reach the cosmic horizon of light, where the light from the first galaxies has taken billions of years to reach us. At this point, we would encounter the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This cosmic microwave background marks the limit of what we can observe directly, but it also provides valuable information about the early universe and the large-scale structure of the cosmos. By studying it, scientists have discovered that the universe is expanding and can estimate its age, composition, and shape. But what if we could go even beyond the cosmic horizon? Beyond the cosmic horizon, the universe continues to expand. This expansion means that distant galaxies are moving away from us at speeds greater than that of light due to the expansion of space itself. This does not violate the laws of physics, since it is space that expands, not the galaxies moving through it. If we could travel beyond the observable universe, we would probably find that the cosmos continues with more galaxies and structures similar to those we see within our observational limits. The uniformity of the CMB suggests that the universe beyond our sight is very same as the universe we can see. However, because the light from these distant regions has not reached us, its exact nature remains a mystery. Music, the idea of an infinite universe, raises some fascinating possibilities. For example, if the universe is truly infinite, there could be an infinite number of galaxies, stars and planets in such a universe. The scale and variety of cosmic objects would be mind-blowing. There could be regions of the universe very different from ours, with different types of stars, galaxies, and perhaps even different physical laws. Another intriguing idea is the concept of a multiverse, in which our universe is just one of many universes that exist. In this scenario, each universe could have its own set of physical laws and constants, leading to a wide variety of possible realities. Some theories suggest that these universes could be connected through wormholes or other exotic phenomena, allowing for the possibility of travel between them. Returning to our analogy of the balloon, imagine the surface of the balloon represents our universe. As the balloon expands, new regions of the surface appear, but the surface itself has no edges. Similarly, as the universe expands, new regions of space can be observed, but the universe itself remains limitless. The idea of a finite but non-finite universe. In this scenario, the universe could be curved in such a way that it repeats itself. This would mean that if you traveled far enough in one direction, you would eventually return to your starting point, much like traveling around the surface of the Earth. This concept is difficult to visualize because we're used to thinking in 3 dimensions, but it is a valid solution to Einstein's equations of general relativity in such a curved universe. There would still be no edges, but the overall shape of the universe would be finite. This idea agrees with some interpretations of the cosmological principle, which suggests that the universe is homogeneous and isotropic on a large scale, but curved in higher dimensions. The exact nature of this curvature, whether positive, negative, or flat, depends on the overall density and composition in cosmology has been the detection of the accelerated expansion of the universe. Observations of distant supernovas and the CMB have shown that not only is the universe expanding, but this expansion is accelerating over time. This acceleration is attributed to a mysterious force known as dark energy, which makes up approximately 68% of the total energy content of the universe. Dark energy has profound implications for the future of the universe. If the expansion continues to accelerate, galaxies will move away from each other at ever-increasing speeds until they become isolated and invisible to each other. This cosmic isolation means that future civilizations in distant galaxies may never know of the existence of other galaxies, as they will be beyond the observable horizon. In short, the edge of the universe is a complex and fascinating concept. Although we cannot see beyond the observable universe, the principles of cosmology suggest that the universe continues in the same way beyond our observational limits. Whether the universe is infinite or finite but without limits, it is likely that it does not have a physical edge. The expansion of the universe driven by dark energy means that our vision of the cosmos will continue to change, revealing more about its vast and mysterious nature. To more deeply understand the concept of the cosmic horizon, we need to discuss the oldest objects found in space. These objects are 3 real galaxies, including Li-11 HD1 and Glass Z13. NL11 is one of the most distant galaxies ever observed. This galaxy is so far away that its light has taken 134 billion years to reach us, which means that we are seeing it as it was only 400 million years after the Big Bang. It is also the most distant galaxy ever discovered. HD1 is another extremely distant galaxy, located about 135 billion light-years away. This galaxy matters because it provides information about the formation of the first stars and galaxies. Another galaxy is the Glass Z13, which has been observed at a distance of about 13,300 million light-years. Like GNZ11 and HG1, this galaxy offers a glimpse of the early universe. Everything we know, see, observe, and interact with as part of the observable universe. Beyond what we can see, much more likely exists. Over time, we will be able to see more as light from distant objects reaches us after traveling for billions of years. Our vision of the universe depends on several factors. First, 138 billion years have passed since the Big Bang. Secondly, the speed of light is the fastest that can travel. We have made amazing measurements about the universe. We know how fast it expands, the density of matter, the amount of normal matter, dark energy, and smaller components like neutrinos, radiation, and black holes. By observing these data, we can find out how big the universe was and how fast it expanded at any time in its history. Today, our observable universe extends about 461 billion light-years in all directions. This distance marks how far light or gravitational waves from the Big Bang would have traveled to reach us. Now, it is much further than the most distant galaxy we have discovered. Simulations suggest the first stars formed between 50 and 100 million years after the Big Bang, and the first galaxies around 200 million years. We have not seen that far yet, but the James Webb Space Telescope could help us soon. The current record for the most distant galaxy is GNZ 11, from when the universe was 400 million years old, only 3% of its current age. This galaxy is 32 billion light-years away, much closer than the edge of the observable universe. The reason for this difference is that the expansion rate of the universe has slowed dramatically over time. When the GNZ 11 galaxy existed, the universe was expanding 20 times faster than it is today. During the cosmic microwave background emission, the expansion was 20,000 times faster, and in the Big Bang it was even faster. According to our best theories, the first true galaxies formed between 120 and 210 million years after the Big Bang, corresponding to a distance of 35 to 37 billion light-years from us. This shows how quickly the universe expanded in its early stages, with 1% of its age accounting for 20% of its total expansion. The expansion of the universe lengthens the wavelength of light, causing the redshift we observe. The size of the current universe shows how time affects it. As time passes, the universe will continue to expand in the future. The distances will increase so much that no galaxies beyond our local group will be seen, not even with powerful telescopes. So we must appreciate the diverse and vast universe that we can see today, since it will not last music forever. But how much of the unobservable universe will we be able to see in the future? The answer is that what we can currently observe is only a small fraction of the entire cosmos. This observable universe is limited by the speed of light and the age of the universe. The light from distant objects has taken billions of years to reach us, but beyond a point known as the cosmic horizon, we can no longer see. However, as time passes, will we be able to see more of the unobservable universe? Let's explore this fascinating question. The observable universe encompasses everything we can see or detect. It is limited by the speed of light and the age of the universe. The light from most distant objects we can see has traveled for approximately 138 billion years to reach us. However, because the universe has been expanding all this time, the observable universe extends far beyond 138 billion light-years. In fact, it reaches about 461 billion light-years in all directions. Imagine you are in a dark field with a flashlight. The light from your flashlight only allows you to see a certain distance. Beyond that point, everything is hidden in the dark. This is similar to our observable universe. We can only see as far as light has traveled to reach us. The universe has been expanding since the Big Bang. This expansion affects our ability to see distant objects as space itself stretches. The light from distant galaxies is stretched or redshifted, making them appear more distant and fainter. This redshift is a key indicator of the rate at which the universe expands. As time passes, light from the most distant parts of the universe will have time to reach us. This gradually expands the observable universe, allowing us to see more of the cosmos. For example, light from a galaxy 461 billion light-years away could reach us in the future further expanding our observable universe. However, there are limits to how much more we can see. The expansion of the universe is accelerating due to a mysterious force known as music, dark energy. This acceleration means that some regions of the universe are moving away from us faster than the speed of light, although the light from these regions is still traveling towards us. The space between us and these regions is expanding so rapidly that the light may never reach us. Cosmic inflation, a rapid expansion of the universe soon after the Big Bang, plays a key role in shaping our observable universe. This inflation stretched space to such an extent that regions that were once very close together became very far apart. This process smoothed any irregularities and gave rise to the uniform universe we observe today. Due to inflation, there are vast regions of the universe beyond our observable horizon that were once connected to our part of the universe. These regions contain galaxies, stars, and possibly other forms of matter and energy that are unseen. Over time, we may be able to observe some of these regions when the light that comes from them finally reaches us. Scientists can learn about the large-scale structure of the universe and the conditions that existed in its early stages by studying the cosmic microwave background. The CMB also offers clues about the universe beyond our observable horizon. The small fluctuations in the CMB's temperature and density provide information about the distribution of matter and energy on large scales. These fluctuations can help scientists infer what lies beyond the observable universe. The unobservable regions are beyond the cosmic horizon, which means that their light has not had enough time to reach us. Over time, some of this light will reach us, expanding our observable universe. However, the accelerated expansion of the universe means some regions will remain unobservable. These regions are moving away from us at a speed greater than the speed of light due to the expansion of space itself. No matter how long we wait, the light from these regions will never reach us. The limits of observability are defined by the combination of the age of the universe, the speed of light, and the rate of expansion. Although we may be able to see more of the universe over time, there will always be regions that will remain beyond our reach. The observable universe will expand, but the unobservable universe will always be larger. After the Big Bang, the universe was filled with matter and energy and expanded rapidly. The rate of expansion and the force of gravity are the two main factors that shape the universe. Expansion pushes everything outward, stretching space and separating galaxies. Gravity, however, pulls everything inward. Normal matter, dark energy, radiation, neutrinos, black holes, and gravitational waves influence expansion. The rate of expansion started high, but it has been slowing down because as the universe expands, its volume increases and the energy density decreases. As the density decreases, so does the speed of expansion, allowing light from distant objects to eventually reach us over time. Galaxies that were once too far away to be seen will enter music, our view, although the Big Bang occurred 138 billion years ago. The expansion of the universe means that objects at a distance of up to 4,610 million light-years are now becoming visible to us within this observable universe. There are about 2 trillion galaxies despite this large number. Our observations do not show an edge in space in any direction. The time elapsed since the Big Bang, the speed of light, and the ingredients of the universe determine what we can observe. Anything farther than 461 billion light-years is currently out of our reach, even if it started moving toward us at the speed of light from the moment of the Big Bang. However, this will change over time, because as time passes, light from more distant objects will reach us, revealing more of the universe. You might think that if we waited long enough, we could see an unlimited amount of the universe, but that is untrue in a universe with dark energy. Dark energy prevents the rate of expansion from falling to zero, but how much of the unobservable universe will we be able to see in the future? The answer is that what we observe is only a small fraction of the entire cosmos. This observable universe is limited by the speed of light and the age of the universe. The light from distant objects has taken billions of years to reach us, but beyond a point called the cosmic horizon, we cannot see anything. However, as time passes, will we see more of the unobservable universe? Let's explore this fascinating question. The observable universe encompasses everything we can see or detect and is limited by the speed of light and the age of the universe. The light from the most distant objects we see has traveled for approximately 138 billion years to reach us. However, because the universe has been expanding during this time, the observable universe extends far beyond 138 billion light years. In fact, it extends about 461 billion light years in all directions. Imagine you are in a dark field with a flashlight. The light from your flashlight only allows you to see a certain distance. Everything beyond that is hidden in darkness. This is similar to our observable universe. We can only see as far as light has traveled. The universe has been expanding since the Big Bang. This expansion affects our ability to see distant objects as space itself stretches. The light from distant galaxies is stretched or redshifted, making them appear farther and fainter. This redshift is a key indicator of the rate at which the universe expands. As time passes, light from the farthest parts of the universe will have time to reach us. This means the observable universe will gradually expand, allowing us to see more of the cosmos. For example, light from a galaxy 461 billion light years away could reach us, further expanding our observable universe. However, there are limits to what we can see. The expansion of the universe is accelerating due to a force known as dark energy. This acceleration means that some regions of the universe are moving away from us at a speed greater than that of light. Although the light from these regions is still traveling towards us, the space between us and these regions is expanding so rapidly that the light may never reach us. Cosmic inflation, a rapid expansion of the universe soon after the Big Bang, plays a key role in shaping our observable universe. This inflation stretched space to such an extent that regions that were once very close together became very far apart. This process smoothed out irregularities and led to the uniform universe we observe today. Due to inflammation, there are vast regions of the universe beyond our observable horizon that were once connected to our part of the universe. These regions contain galaxies, stars, and perhaps other forms of matter and energy that we cannot see. Over time, we may be able to observe some of these regions when the light that comes from them finally reaches us. Measuring distances in space is fascinating. Unlike measuring distances on Earth, we cannot simply use a ruler or measuring tape. Instead, astronomers use a variety of methods and tools to learn how far away objects such as stars, planets, and galaxies are from us. These methods rely on the properties of light, the movement of celestial objects, and mathematical calculations. In this script, we will explore the techniques used to measure cosmic distances and how they help us grasp the immensity of the universe. Precise distance measurements also let us calculate the age of the universe and study the expansion of space and dark energy's behavior. One of the key methods for measuring distances to nearby stars is parallax. Parallax is the apparent change in an object's position when viewed from different locations. You can see this effect by extending your thumb at arm's length and looking at it with one eye closed. By switching eyes, your thumb appears to move with respect to the background. This same principle is used to measure distances to stars. Astronomers use the Earth's orbit of the Sun as a reference. By observing the position of a star at different times of the year, they can measure the small displacement of its position with respect to the background of more distant stars. This displacement is called the parallax angle. The smaller the angle, the farther away the stars are. Parallax works best for stars within a few hundred light years of Earth. For more distant objects, other methods are needed to measure distances beyond parallax. Astronomers use a unit called parsec. A parsec is the distance at which a star would show a parallax angle of 1 arcsecond. The parsec is equivalent to about 326 light years, or roughly 31 trillion kilometers. The term parsec combines parallax and second for objects beyond the reach of parallax measurements. Astronomers use standard candles. A standard candle is an astronomical object with a known luminosity or intrinsic brightness. By comparing the known luminosity with the observed brightness, they can calculate distance. This method relies on the inverse square law of light, which says that an object's brightness decreases with the square of the distance from the observer. One of the most important standard candles is the Cepheid variable star. Cepheid variables are pulsating stars whose brightness varies in a regular pattern. The period of their brightness variations relates directly to their luminosity. By measuring the period of Cepheids' pulsations, astronomers can determine their luminosity. By comparing this with the observed brightness, they can calculate the star's distance. Cepheid variables are crucial for measuring distances within our galaxy and to nearby galaxies. Another valuable standard candle is the Type I supernova. These supernovas occur in binary star systems where one star is a white dwarf. When the white dwarf accumulates enough material from its companion star, it reaches critical mass and explodes in a bright supernova. Type I supernovas have a consistent maximum luminosity, making them excellent standard candles for measuring distances to distant galaxies. In the 1920s, Edwin Hubble made a revolutionary discovery. He observed that galaxies are moving away from us, and the farther away they are, the faster they move. This relationship is known as Hubble's law and can be expressed by measuring the redshift of a galaxy's light. Astronomers can determine its velocity. The redshift occurs because the wavelength of light is stretched as the galaxy moves away from us, causing the light to appear redder. Using Hubble's law, they can calculate the galaxy's distance. This method is especially useful for measuring distances to galaxies millions or billions of light years distant. Redshift is a key tool for measuring cosmic distances. It happens when the wavelength of light from an object lengthens due to the universe's expansion, causing the light to appear redder. The greater the redshift, the farther away the object is, and the faster it moves away from us. By measuring the redshift of a galaxy's light, astronomers can determine its velocity and, using Hubble's law, calculate its distance. The methods described above form what we know as the cosmic distance ladder. This consists of different steps, each representing a method to measure distances on different scales. The lower steps, like parallax, are used for nearby objects. The intermediate steps, like standard candles, extend to more distant objects. The upper steps, such as redshift and Hubble's law, reach the farthest parts of the observable universe. Each step of the ladder builds on the previous one, which allows astronomers to measure distances across vast scales. For example, parallax measurements calibrate the distances to CI variables, which then calibrate the distances to TI supernovas, and so on. This hierarchical approach ensures accuracy and consistency in measuring cosmic distances. The gravitational lens is another method for measuring cosmic distances. It occurs when the gravitational field of a massive object, like a galaxy cluster, deflects light from a more distant object. This effect, predicted by Einstein's theory of general relativity, can magnify and distort the light, creating multiple images of the distant object. By analyzing the properties of the lensed images, astronomers can determine the mass of the object acting as a lens and the distance to both the lens and the background object. Gravitational lenses provide valuable information about the distribution of mass in the universe, including dark matter, and help to refine distance measurements. The cosmic microwave background is the oldest light in the universe, dating to about 380,000 years after the Big Bang. It provides a snapshot of the early universe and contains valuable information about its size, shape, and composition. By studying the CMB, scientists can infer the distance to the edge of the universe and learn about the cosmos' large-scale structure. The CMB also serves as a reference for measuring other cosmic distances. For example, observations of the CMB have refined the value of the Hubble constant, improving the accuracy of distance measurements across the universe. These are some of the techniques for measuring cosmic distances. Basic trigonometry, similar to what you studied in high school math class, can be used to measure things that are quite close, such as those in our solar system, and even in our small neighborhood of the Milky Way. Less than 100 light-years with the help of the parallax method, the distance of distant objects can be measured or estimated. Imagine looking at your finger through your left eye or closing your right eye, and then switching eyes. You would notice that the position of your finger appears to change with respect to a point on the wall. This is called parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger using trigonometry. When it comes to measuring distances to other stars, Earth's orbit around the Sun provides a baseline for the calculations. Simply, if you take the position of a star once a year at a point in the sky, and then again 6 months later, you will have a relative position of the nearby object in relation to the much more distant stars. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of Earth's orbit and the angle of the light in those two measurements. Once trigonometry is no longer useful, astronomers look for Cepheid stars, which are extremely bright and common. These specific stars were first identified in 1794 and can pulse, becoming fainter and brighter in predictable cycles. Surprisingly, the longer it takes a SCI to pulse, the brighter the star actually is. Similarly, the shorter the duration of the pulsation, the fainter the star is. These pulsations are directly related to its absolute luminosity and occur in well-defined and predictable periods, ranging from 1 to 100 days, just as if you saw a candle right in front of you and another far away. The closer one would seem much brighter. Therefore, the actual brightness of these stars can be determined and, consequently, their distance by measuring nearby Cepheids and comparing the duration of their pulsation period with that of the Cepheids that are farther away. CI variables can be seen and measured at a distance of about 20 million light-years, compared to a maximum distance of about 65 light-years for parallax measurements from Earth and just over 3,260 light-years for the HIP mission. They serve as standard distance markers, which is another crucial step in the cosmic distance scale. Although 20 million light-years sounds an enormous distance, the cosmos is 1,000 times larger, so we need to add another rung to the ladder. This is where supernovas, especially those of certain binary star systems, come in handy. One of the stars in these binary systems dies and becomes a white dwarf, while the other star continues to exist. The white dwarf begins to consume the surviving star and gets bigger until it is about 14 times the mass of the Sun. At that moment, a massive explosion occurs that releases more energy than entire galaxies and is visible in more than half of the observable universe. We refer to this as a type I supernova. Astronomers can determine the absolute brightness of the explosion and, consequently, the approximate cosmic distance to those distant galaxies because we know how much mass is exploding at even greater distances, tens of billions of years. The Hubble constant comes into play, named after Edwin Hubble. This is the unit of measure of the universe's expansion. The universe has been getting bigger since the Big Bang initiated its growth. The universe is expanding, and the speed of this expansion is determined by the Hubble constant. The farther away a galaxy is, the faster it appears to be moving away from us. This phenomenon is known as redshift, which is similar to the Doppler effect experienced with sound waves. Redshift occurs because waves affected by their movement through space and air carry both sound and light. Sound travels through the air at a maximum speed of 750 miles per hour or 1,200 kilometers per hour. Sound waves in front of an ambulance are compressed as it moves forward and sounds its siren. Meanwhile, the sound waves behind the ambulance begin to propagate. This means that the frequency of the sound waves is higher in front of the ambulance and lower behind it. Our brain interprets pitch changes as variations in the frequency of sound waves. Like sound, light is a wave that moves at a fixed speed of 186,000 meters per second or 300,000 kilometers per second, about 1 billion kilometers per hour. Therefore, light follows the same rules as sound. Galaxies, as we know, move away from us in a similar way to how an inflated balloon would cause a wave created by stretching its fabric. The wavelength of the light stretches when the galaxies move away from us through the use of a prism or a suitable similar instrument, such as a telescope or diffraction gratings, we can see a series of absorption lines of elements such as sodium, hydrogen, etc. All those absorption lines experience a Doppler shift and move towards the red part of the spectrum. If a galaxy moves away from us, we call this redshift. The opposite occurs with galaxies that move towards us. They shift towards the blue. Astronomers often use just the expression redshift to simplify things. If a blue shift occurs, they simply place a negative sign before it. The shift of a galaxy increases with its distance from Earth. So the redshift of a galaxy on the cosmic horizon, the outer edge of our observable universe, is almost infinite. This indicates that the light from that distant galaxy has very little energy, so we can hardly see those galaxies in the visible light spectrum. When Hubble observed the light from distant galaxies through a prism, he observed a redshift away from the known variables. For the Hubble discovered that almost all the galaxies he examined had this redshift, indicating that they were moving away from us at extremely distant distances. The distances between galaxies could be determined accurately by plotting several redshifts and known distances on a graph. Measuring distances in space is fascinating. Unlike measuring distances on Earth, we cannot simply use a ruler or tape measure. Instead, astronomers use various methods and tools to determine how far away objects such as stars, planets, and galaxies are from us. These methods are based on the properties of light, the movement of celestial objects, and mathematical calculations. In this script, we will explore the different techniques used to measure cosmic distances and how they help us understand the immensity of the universe. The precise measurement of distances also allows us to calculate the age of the universe and study the expansion of space and the behavior of dark energy. One of the fundamental methods for measuring distances to nearby stars is parallax. Parallax is the apparent shift in an object's position when viewed from different locations. You can see this effect by extending your thumb at arm's length and looking at it with one eye closed, then switching eyes. Your thumb appears to move against the background. This same principle is used to measure distances to stars. Astronomers use the Earth's orbit around the Sun as a reference. By observing the position of a star at different times of the year, they can measure the small shift in its position with respect to the background of more distant stars. This shift is called the parallax angle. The smaller the angle, the farther away the stars are. Parallax is most effective for stars within a few hundred light years of Earth. For more distant objects, other methods are needed to measure distances beyond parallax. Astronomers use a unit called a parsec. A parsec is the distance at which a star would show a parallax angle of 1 arcsecond. A parsec is equivalent to about 326 light years, or approximately 31 trillion kilometers. The term parsec combines parallax and arcsecond, which means beyond. For objects beyond the reach of parallax measurements, astronomers use standard candles. A standard candle is an astronomical object with a known luminosity or intrinsic brightness. By comparing the known luminosity with the observed brightness, they can calculate the distance. This method is based on the inverse square law of light, which states that an object's brightness decreases with the square of the distance from the observer. One of the most important standard candles is the Cepheid variable star. Cepheid variables are pulsating stars whose brightness varies in a regular pattern. The period of their brightness variations is directly related to their luminosity. By measuring the period of the pulsations of a Cepheid, astronomers can determine its luminosity. By comparing it with the observed brightness, they can calculate the star's distance. Cepheid variables are crucial for measuring distances within our galaxy and to nearby galaxies. Another valuable standard candle is the Type I supernova. These supernovas occur in binary star systems where one star is a white dwarf. When the white dwarf accretes enough material from its companion star, it reaches a critical mass and explodes in a bright supernova. Type I supernovas have a constant maximum luminosity, making them excellent standard candles for measuring distances to distant galaxies. Edwin Hubble made a revolutionary discovery in the 1920s. He observed that galaxies are moving away from us, and the farther away they are, the faster they move. This relationship is known as Hubble's law and can be expressed by measuring the shift of light from a galaxy. astronomers could determine its velocity. Redshift occurs because the wavelength of light is lengthened as the galaxy moves away from us, making the light appear redder. Using Hubble's law, they can calculate the galaxy's distance. This method is particularly useful for measuring distances to galaxies millions or billions of light years away. Redshift is a crucial tool for measuring cosmic distances. It occurs when the wavelength of light from an object is stretched due to the expansion of the universe, making the light appear redder. The greater the redshift, the farther away the object is, and the faster it moves away from us. By measuring the redshift of the light from a galaxy, astronomers can determine its velocity and, using Hubble's law, calculate its distance. The methods described previously form what is known as the cosmic distance ladder. This ladder consists of different rungs, each representing a method for measuring distances on different scales. The lower rungs, such as parallax, are used for nearby objects. The intermediate rungs, such as the standard candles, extend to more distant objects. The upper rungs, such as redshift and Hubble's law, reach the farthest parts of the observable universe. Each rung of the ladder is based on the previous one, allowing astronomers to measure distances across vast scales. For example, parallax measurements calibrate distances to 5 variables, which in turn calibrate distances to Ti, a supernova, and thus in this hierarchical approach, precision and consistency in measuring cosmic distances is guaranteed. Gravitational lensing is another method used to measure cosmic distances. It occurs when the gravitational field of a massive object, such as a cluster of galaxies, deflects the light from a more distant object. This effect, predicted by Einstein's theory of general relativity, can magnify and distort light by creating multiple images of the distant object. By analyzing the properties of the lens images, astronomers can determine the mass of the object acting as a lens and the distance to both the lens and the background object. Gravitational lensing provides valuable information about the distribution of mass in the universe, including dark matter, and helps to refine distance measurements. The cosmic microwave background is the oldest light in the universe, dating back to about 380,000 years after the Big Bang. It provides a snapshot of the early universe and contains valuable information about its size, shape, and composition. By studying the CMB, scientists can deduce the distance to the edge of the observable universe and learn about the large-scale structure of the cosmos. The CMB also serves as a reference point for measuring other cosmic distances. For example, CMB observations have helped refine the value of the Hubble constant, improving the accuracy of distance measurements across the universe. These are some of the technological techniques for measuring cosmic distances. Basic trigonometry, similar to what you studied in high school math class, can be used to measure things that are quite close, such as those in our solar system and even in our small neighborhood of the Milky Way. Less than 100 light-years with the help of the parallax method can be measured or estimated. Imagine you look at your finger with your left eye, or close your right eye, and then switch eyes. You will notice that the position of your finger appears to change with respect to a point on the wall. This is called parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger using trigonometry. When it comes to measuring distances to other stars, the Earth's orbit around the Sun provides the baseline for these calculations. Simply, if you take the position of a star once a year at a point in the sky, and then do it again 6 months later, you will have a relative position of the nearby object in relation to the much more distant stars in the sky. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of Earth's orbit and the angle of light in those two measurements. Once trigonometry is no longer a useful technique, astronomers look for Cepheid stars, which are extremely bright and common EXT stars. These specific stars were first identified in 1794 and have the ability to pulsate, becoming fainter and brighter in predictable cycles. Surprisingly, the longer it takes a SCI to pulsate, the brighter the star actually is. Similarly, the shorter the pulsation, the fainter the star. These pulsations are directly related to their absolute luminosity and occur in well-defined and predictable periods of time, ranging from 1 to 100 days, just as if you saw a candle right in front of you and another far away. The one that is closer would seem much brighter. Therefore, the actual brightness of these stars can be determined and, consequently, their distance by measuring nearby seeds and comparing the duration of their pulsation period with those of the more distant sates. CI variables can be seen and measured at a distance of about 20 million light-years, compared to a maximum distance of about 65 light-years for parallax measurement from Earth and just over 3,260 light-years for the HIP-PAROS mission. They serve as standard distance markers, which is another crucial step in the cosmic distance scale. Although 20 million light-years seems like a huge distance, the cosmos is 1,000 times larger, so we need to add another rung to the ladder. This is when supernovae, especially those from specific binary star systems, come in handy. One star in these star systems dies and becomes a white dwarf, while another star continues to exist. After that, the white dwarf begins to consume the surviving star and grows larger until it reaches approximately 14 times the mass of the Sun. At that point, a massive explosion occurs that releases more energy than entire galaxies and is visible in more than half of the observable universe. We refer to this as a type A supernova. Astronomers can determine the absolute brightness of the explosion and, consequently, the approximate cosmic distance to those distant galaxies, since we know how much mass is exploding at even greater distances, tens of billions of years. The Hubble constant comes into play, named after Edwin Hubble, which is the unit of measurement of the expansion of the universe. The universe has been getting bigger since the Big Bang started its growth. The universe is expanding, and the speed of this expansion is determined by the Hubble constant. The farther away a galaxy is, the faster it seems to move away from us. This phenomenon is known as redshift, which is similar to the Doppler effect experienced with sound waves. Redshift occurs because waves that are affected by their movement through space and air carry both sound and light. Sound travels through the air at a maximum speed of 750 m per hour or 1,200 kilometers per hour. Sound waves in front of an ambulance are compressed as it moves forward and sounds its siren. The sound waves behind the ambulance, meanwhile, begin to propagate. This means that the frequency of the sound waves is higher in front of the ambulance and lower behind it. Our brain interprets pitch changes as variations in the frequency of sound waves, similar to sound. Light is a wave that moves at a fixed speed of 186,000 meters per second or 300,000 kilometers per second. That is about 1 billion kilometers per hour, so light follows the same rules as sound. Galaxies, as we know, are moving away from us in a similar way to how an inflated balloon would cause a wave created by stretching its fabric. The wavelength of light stretches when galaxies move away from us. Through the use of a prism or a comparable instrument such as diffraction gratings, we can see a series of absorption lines of elements such as sodium, hydrogen, etc. All those absorption lines, however, experience a Doppler shift and move towards the red part of the spectrum. If that galaxy moves away from us, we call this redshift. The opposite occurs with galaxies that move towards us. They shift towards the blue. Astronomers often use the term redshift to simplify things. If a blue shift occurs, they simply place a negative sign before it. The shift velocity of a galaxy increases with its distance from Earth. As a result, the redshift of a galaxy on the cosmic horizon, the outer edge of our observable universe, is nearly infinite. This indicates that the light coming from that distant galaxy has very little energy, so we can barely see those galaxies in the visible light spectrum. When Hubble observed the light from distant galaxies through a prism, he observed a redshift away from the known color variables. Hubble discovered that almost all the galaxies he examined had this redshift, indicating that they were moving away from us at extremely great distances. The distances between galaxies could be determined accurately by plotting several redshifts and known distances on a graph. Already in the 4th century BC, a Greek scholar named Aratus imagined reaching the edge of the known universe and trying to extend his hand beyond it. He believed that if there was nothing beyond, then the universe must be infinite. In the 16th century, An Italian philosopher named Giordano Bruno also believed that the universe was infinite and full of countless stars and planets. In the 17th century, the English philosopher Thomas Hobbes thought that it made no sense to speculate about an infinite universe beyond what we can see, because we could not measure or understand it. He suggested that people focus on what could be observed and understood. His practical approach has influenced scientists even today, who often say that speculating on these issues is not very useful. Despite the risk of getting lost in such deep questions, some modern cosmologists continue to explore these ideas with the help of current technology and centuries of accumulated knowledge in science, mathematics, and philosophy. Our understanding of the universe is like looking from an island. We can only see as far as the horizon. Light travels at a constant speed, so when we look at space, we are also looking back in time. We can see galaxies that existed 1,000, 5,000, or even 10,000 million years ago. The limit of what we can observe is defined by this limit in time, not only space. It is like a mark of how far light has traveled since the first galaxies appeared. Those first galaxies whose light has been traveling for 138 billion years are now much further away, about 46 billion light-years away, due to the universe's expansion. When we look as far as we can in the universe, there is nothing in the distant galaxies that suggests that they are colliding against any kind of limit, despite the early expectations of a universe that began without anything. What we see on a large scale is surprisingly uniform. Space seems to expand uniformly in all directions without a central point. On scales larger than about 230 million light-years, everything we see is more or less the same. There are no significantly hotter, colder, or more populated regions of galaxies than others, despite the apparent immensity of the universe, with its 92 billion light-years in diameter. The uniformity suggests that it could be even larger to accommodate any initial imperfections that inflation has smoothed out. However, as the English philosopher Thomas Hobbes pointed out, there is a limit to what we can learn about these distant regions. No technology can overcome the barriers imposed by the speed of light. However, we possess an unlimited imagination, and it is in our nature to reflect on what could be beyond the visible universe, even if these speculations do not lead to concrete answers. Let's imagine a person from the Amazonian tribe venturing into the ocean. If he sails long enough, he could end up back at the starting point without ever finding a limit or edge. This is because the Earth is round and its surface curves on itself, creating a finite but borderless two-dimensional space. Cosmologists suggest that our three-dimensional universe could be curved in a similar way, such that, although finite, it has no borders. To test this idea involves understanding how geometry works in different spaces. On a flat surface, parallel lines remain parallel forever. On a sphere like Earth, parallel lines eventually meet. On a saddle-shaped surface, parallel lines separate. In the 1930s, Edwin Hubble attempted to apply this logic to the universe by counting galaxies along a line of sight to see how their number changed with distance. However, as looking further into space also means looking back in time, the evolution of galaxies complicates these counts. Today, astronomers use better methods and tools, such as standard rulers, to compare their models of the shape of the universe with what we observe. Projects such as the Wilkinson Microwave Anisotropy Probe have measured the total mass and energy of the universe by comparing them with critical values that would determine whether the universe will expand forever or eventually collapse, by examining slight irregularities in the cosmic microwave background that fills space. Astronomers are looking for any sign of curvature. Discovering whether space is curved positively or negatively, or even a mixture of both, would help us understand the true size and shape of the universe, which would support the idea of an infinite but borderless cosmos. Similarly, the instruments that scientists use to observe the universe have their limits. This suggests that, although the universe appears flat from our current perspective, we may not be close enough to see its true shape. The flatness we observe establishes a minimum size for the part of the universe that we cannot see. If the universe has a curve but appears flat, it must be at least 27 trillion light-years in diameter, thousands of times larger than the part we can observe. It is a great distance, and it is only the smallest possible size that the universe could have. It could be even larger, perhaps infinite. In 1980, Mandelbrot was one of the first to use computer graphics to visualize concepts that could not be easily drawn by hand. He used simple equations to create images of a new type of geometry that he called fractal, from the Latin word meaning broken or shattered glass. Fractals are structures that look similar no matter how much they are enlarged or moved away, always revealing more details and never becoming simpler, meaning they have infinite complexity. Using computers, Mandelbrot created what is now known as the set of Mandelbrots to demonstrate this idea. But he also pointed out that similar patterns are found in nature, such as in the leaves of ferns and even in the way galaxies cluster together. He wondered if the entire universe could be a fractal. Although we now know that at the largest scales we can see the universe looks almost the same everywhere, but could fractal-like patterns exist beyond what we can currently observe? While we may not be able to answer how much the universe extends, it is beyond our observable limits at this time. Even starting with what we can see, we quickly come across the idea of infinity again. Our universe is expanding with everything moving away from everything else, much like a loaf of bread rising in an oven. If the universe began at an infinite point, our observable universe was only a small part of that infinite expansion over time. Although our observable universe gets bigger, it is actually just a measure of the distance that light has traveled over time. The actual physical universe is becoming less dense, while larger structures, such as galaxies, are held together by gravity. All galaxies beyond our local group are moving away at an average speed of 70 kilometers per megaparsec. Looking to the future, if no new forces intervene, the universe will continue to expand. The galaxies will move further and further away, and eventually even the stars will move away from each other, leading to a state known as the heat death of the universe. However, there is no single event that ends the universe. Our observable universe will continue to expand, potentially becoming infinitely large due to the nature of infinity. It would take an infinite amount of time to reach this state, and we could still only explore a finite part of it, as the universe expands faster than we can explore it. When we look back in time, the expansion of the universe is reversed. The universe becomes smaller, denser, and hotter until it does not resemble the universe we know today. At this stage, the laws of physics begin to behave strangely. We can only begin to understand the universe once it gets bigger, and at sizes smaller than a Planck length, our known physics no longer works. The universe could have started expanding from an infinitely small, dense, and hot point. We don't know what it would be like or how it would behave. Our observations and models do not suggest any other type of beginning. Thinking of the universe as infinitely old and expanding from an infinitely small point challenges our understanding based on what we see now. We cannot refute the theory that the universe could continue to expand forever. This raises questions about how to reconcile our Big Bang models with the idea of an infinitely large universe. The universe we can see is expanding, but that may not be true for the entire universe at all times. Cosmologists like Alan Guth and later Andre Linde have suggested that what we see could be just a small expanding region within an infinitely large universe. This concept, known as eternal inflation, proposed in 1979, suggests that our universe is just one of countless bubble universes within an infinite cosmic expansion. Each of these bubble universes could be in a different phase of development and could even operate under different physical laws. This idea leads to the concept of a multiverse in which infinite universes exist, each with its own set of physical rules. The exploration of these theories introduces even more complexity, especially when considering theories such as M-theory, a type of string theory. This theory suggests that our reality is just one of the many layers that exist briefly, where dimensions intersect within a vast hyperspace. Then we have to think not only of infinite universes in our three dimensions, but of a multiverse with countless dimensional combinations. Each of these universes could have different physical constants, such as gravity or the mass of particles, which opens up unlimited possibilities. Our Big Bang could be just a small detail in the eventual heat death of our universe, a big detail in a much larger scheme. Roger Penrose's idea of conformal cyclic cosmology is yet another layer. It suggests that when our universe seems infinitely large, it could actually be starting a new universe on a completely different scale. Music, according to these investigations, our universe could be just a bubble within a sea of many universes whose physical laws differ from place to place, encompassing all physical possibilities. British physicist Brian Cox has discussed how the idea of the simultaneous existence of multiple universes fits into the framework of what is known as eternal inflation. This theory expands on the concept of the Big Bang by suggesting that the universe we observe is just one of many bubbles in a frigid sea of space-time. These bubble universes are not static, but are continuously being formed. The process of forming each bubble universe begins when a particular region of space stops its rapid inflation. However, the theory of eternal inflation suggests that not all parts of space-time stop inflating at the same time. Some regions continue to experience inflation, leading to the perpetual creation of new universes. Each of these universes may have completely different physical laws, potentially different from anything we can observe ourselves. To better visualize the multiverse theory, imagine an immense library filled with a large number of books. Each book in this library represents a different universe. If this library really contains an infinite number of books, then all possibilities exist in one of them. In one of these stories, for example, the physical constants that we take for granted, such as gravity or the speed of light, could be slightly altered in a book. Gravity could be weaker, causing creatures to grow taller and buildings potentially taller. In another, the speed of light could be slower, profoundly affecting the way light and energy move through that universe. But the variations between these universes extend beyond the laws of physics. They could include completely different courses of history and evolution. Let's imagine a universe in which dinosaurs never faced extinction, allowing them to evolve into the dominant species. Or let's think of a universe in which the fundamental elements of matter are different, giving rise to planets and stars composed of substances such as dark matter. But is there any proof of the existence of a multiverse, or are we a bubble within it? In the book Endless Universe Beyond the Big Bang, the authors Paul Steinhardt and Neil Turok propose an idea. They hypothesize that the universe did not begin with a single Big Bang, but suggest a model that involved infinite cycles of cosmic events that could include collisions with other bubble universes. This theory coincides with the findings of researcher R. Ranga Ramchari in 2015 proposed that our universe could have collided with another. Cherry's study of the cosmic microwave background radiation revealed unusual signals hinting at such cosmic interaction, though it is not yet clear whether this contact was minor or significant. The CMB, often called the glow of the Big Bang, is essentially the oldest light detectable by modern instruments. It is like a snapshot of a universe's childhood captured billions of years ago, helping scientists reconstruct how the universe has expanded and evolved. This leads us to consider how the CMB might indicate the existence of a multiverse. When astronomers analyze the CMB, they observe not just a constant breath, but a complex pattern of light and dark spots. These spots show tiny temperature differences that play a key role in the formation of the large-scale structure of the universe as we know it. However, some characteristics of the CMB, such as the cold spot, a large area with below-average temperatures, have puzzled researchers. An intriguing theory about the cold spot is that it could be a kind of cosmic bruise, a vestige of an era when our universe came into close contact with another universe. This hypothesis suggests that such interactions could be evidence of multiple universes brushing against each other, supporting the broader concept of a multiverse, where a universe is just one of many. In 2007, theoretical physicist Laura Mersini-Houghton and her team posed a hypothesis about the cold spot observed in the cosmic microwave background. They suggested that this large, colder region could be proof that our universe interacted with another universe. According to their theory, if multiple universes exist, they could collide occasionally, and such collisions could leave detectable marks very similar to bruises. Laura Mersini-Houghton proposes that the cold spot could be one of these cosmic bruises caused by the gravitational effects of an adjacent universe. This nearby universe could have exerted a gravitational force strong enough to slightly slow the expansion in that specific area of our universe, resulting in the colder temperatures we observe. This idea aligns closely with the findings of Ranga Ramchari in 2015. Cherry suggested certain patterns in the CMB as possible indications of a past collision with another universe, describing them as a bruise of said encounter. Mersini-Houghton also suggests that the interaction between universes could cause fluctuations in inflation, leaving scars or dents in the fabric of our cosmos. She believes that these scars from the interactions between universes could be visible as anomalies, such as the cold spot. Fast-forwarding to more recent times, these hypotheses lead to predictions about what other similar anomalies might look like. A key aspect of the theory of cosmic inflation is the expectation that everything in the universe should be evenly distributed across the sky. However, the presence of anomalies, such as the cold spot, challenges this notion, suggesting a potentially more complex history for our universe. These observations and theories raise profound questions about the very nature of our universe. They question the traditional view that the Big Bang was the absolute beginning. Instead, they raise the possibility that the Big Bang could have been a transition phase of a previous universe, or that perhaps the universe existed in some form before the events that we consider the beginning. The anomalies observed in the cosmic microwave background radiation suggest that our understanding of the origin of the universe may have to be revised to favor these new ideas. Sir Roger Penrose's conformal cyclic cosmology model presents a view of the universe where each cycle or era begins with a Big Bang and is followed by a period of expansion. During this phase, matter and radiation spread out and cool as the universe expands. The cosmic microwave background becomes fainter, and the galaxies move away from each other, driven by the increasing dominance of dark energy in this model. As the universe approaches a state of cold and disordered vacuum, traditional notions of time lose their meaning. In this final cold and empty state, the universe undergoes what is called a conformal rescaling. This process involves adjusting the scale of the universe while preserving the angles between points. Penrose uses this concept to suggest that something infinitely large, like the space-time of our universe, can be mathematically transformed into something finite. This transformation allows the end of a universal cycle to connect perfectly with the beginning of another. This cyclic model implies that the universe has no definite beginning or end, and that the structures we observe in the cosmos are natural results of this continuous process. One of the most compelling aspects of Penrose's theory is its potential for obtaining observational evidence. He suggests that certain circular patterns observed in the cosmic microwave background, known as Hawking points, could be remnants of previous cosmic cycles. These points, named after physicist Stephen Hawking, are believed to be footprints left by black holes that existed in a past aeon and have since evaporated, leaving their mark on the cosmic microwave background radiation. The scientific community remains divided on the accuracy of studies claiming to have identified possible Hawking points in the cosmic microwave background data. Some researchers argue that further research is needed to confirm or refute these findings, suggesting that the observed patterns could be coincidental or caused by instrumental artifacts. If validated, the conformal cyclic cosmology model proposed by Roger Penrose would drastically alter our understanding of the universe. This model introduces a cyclic conception of a universe that challenges the traditional view of a singular beginning and offers new perspectives on the nature of time, cosmic evolution, and the ultimate fate of the universe. It also raises profound questions about the role of information, causality, and entropy throughout the eras. Future research is likely to aim at refining this model and seeking stronger observational evidence. The James Webb Space Telescope is already providing valuable data that could test the predictions made by conformal cyclic cosmology. In addition, advances in theoretical physics, such as the development of a quantum theory of gravity, could help harmonize this model with other cosmological theories, unlike the Big Bounce theory, where the expansion of the universe eventually stops and reverses into contraction before starting anew. Conformal cyclic cosmology postulates continuous expansion. This continuous expansion is fundamental to its cyclic process. Recent advances in physics and cosmology have provided possible indications of cosmic cycles within the CMB, showing events that may have occurred in previous eons. In addition, the enigmatic components of our universe, namely dark energy and dark matter, continue to baffle scientists. Some theories suggest that these elements could play a crucial role in the cycles of the universe, with dark matter as a possible catalyst for the final contraction of the universe, and dark energy driving its accelerated expansion. The discovery of gravitational waves from collisions of black holes and neutron stars has revealed new aspects of the universe. The researchers are now exploring whether these waves can offer clues about possible cyclical patterns of the universe and help evaluate various cyclical cosmological models. The idea of a cosmic cycle, rooted in both modern science and ancient philosophy, profoundly influences our understanding of the universe and our place in it. If the universe works in a continuous loop, this challenges traditional views of linear time and the singularity of our existence, provoking profound reflections on time itself and the broader meaning of life. The study of the cosmic cycle could also shed light on the fundamental laws that govern the universe. The ancient concept of a repetitive cosmos could be crucial to solving some of the mysteries of the universe. This concept suggests that the universe endlessly recreates itself, offering valuable perspectives on the nature of existence. String theory suggests that what we perceive as elementary particles could actually be strings of energy vibrating in multiple dimensions beyond our usual space. According to these theories, these additional dimensions are compactified, which means that they are so rolled up that, even if we could access them by traveling along these dimensions, we would quickly return to our starting point. But what if these hidden dimensions could contain whole universes? Introduced in the early 2000s, the ekpyrotic model of the universe suggests precisely that. According to this theory, we could live on a three-dimensional membrane that exists alongside others within a larger space of 4 dimensions plus time. Occasionally, our universe could collide with another that possibly houses a different universe. If such collisions were to occur, this could explain both the beginning and the future end of our universe. In this model cycle, the branes move towards and away from each other, colliding and separating again and again in each cycle, from the Big Bang to expansion, through the Big Crunch, and back to the Big could seed the structures we observe in the universe today, such as galaxies and clusters. These structures could be the result of the interactions between the branes during their slow approach before a new Big Bang occurs. Although introducing concepts of additional universes and higher dimensions to explain cosmic origins may seem radical, there are compelling reasons why physicists are seriously considering these ideas. While we search, we lack concrete evidence that phenomena, such as the collision of universes or the broader concept of inflation, actually occurred. The idea of colliding universes, as proposed in some inflationary theories, suggests that 2 bubble universes could impact each other, leaving detectable marks on their cosmic background radiation, similar to bruises. The theory of eternal inflation postulates that while the greater cosmos continuously expands, inflation occasionally stops in localized areas. This causes those regions to heat up and transition to standard cosmic expansion, potentially creating multiple bubble universes, each part of a vast multiverse. Despite extensive astronomical searches, no definitive signs of these collisions have been detected. Researchers continue to explore these possibilities over time. Another theory that attempts to explain our cosmic origins has been revised. Its latest versions move away from scenarios involving cosmic collisions and higher dimensions, aligning more closely with theories of the infrared. Now, this model suggests that the dynamics of a scalar field, a type of energy field believed to drive cosmic inflation, could be responsible for the behavior of the universe, which goes from a state of collapse to a new Big Bang without the need for dramatic collisions between branes. The cosmic horizon marks the limit of our observable universe and represents a firm limit of what we can see as the universe expands. This limit recedes further and further, taking with it everything beyond W at ever-increasing speeds, ensuring that its light can never reach us, while we can never fully determine what exists beyond this limit. All theories suggest that our observable universe is only part of a much larger and possibly more complex space. This larger space could contain a multiverse with different physical laws form part of a cosmic cycle that repeats endlessly or of extended dimensions beyond our current understanding. The truth remains elusive, and our concepts of the universe continue to evolve as we delve into these cosmic mysteries. We are continuously gathering clues to understand the fundamental structure of the universe and its earliest moments through patterns observed in the cosmic microwave background, the distribution of galaxies, and gravity and particle physics experiments. We are gaining insights that bring us closer to narrating the complete story of the cosmos. We can already glimpse the fiery conditions of the moments of the universe's birth after its beginning with the data we are collecting. We hope to be able to follow the narrative of the universe from its fiery beginning to its eventual conclusion. Our understanding of the universe has expanded dramatically throughout human history. The beauty of science lies precisely in recognizing how much we have left to learn. Some of the brightest minds are exploring profound questions about the nature of the universe and what might lie beyond its limits. This research explains more about how we define the universe. Is it everything that exists, or is it simply part of a broader reality? Could other universes like ours exist? The possibilities are endless, from entire worlds hidden inside black holes to completely separate universes. Our innate curiosity, the ability to dream, and the ability to marvel to drive these explorations. We have developed numerous theories about what could exist beyond or be larger than our known universe. Theories that align with existing observations, physics, and mathematics. When we look at the stars, it is important to remember that our curiosity knows no limits. The universe, whether finite or infinite, invites us to explore, seek answers, dream, and think about the concept of the observable. The universe, which is only a small fraction of a much larger cosmos, opens up endless possibilities. It suggests that what we see is not all there is, that beyond our cosmic observation, there could be other time spaces full of galaxies, stars, and planets potentially governed by laws of physics different from ours. These regions could be part of a larger multiverse where each universe is a separate bubble floating in a high-dimensional space. The idea of the simultaneous existence of multiple universes challenges our perception of reality and underscores the possibility that our universe is only one of an infinite number of universes, each with its own unique properties and histories. In these other universes, the constants and laws that could sustain the fabric of reality could vary drastically. The strength of gravity, the nature of electromagnetism, the ISM masses of elementary particles, and the behavior of dark energy could be different, giving rise to universes that are completely divergent from our own. Some could be teeming with life, while others could be inhospitable. The fundamental forces that shape their structures could give rise to complex phenomena that are unimaginable in our own universe. The theoretical frameworks that allow these possibilities include string theory and its extensions, which posit that our universe could be one of many branes, three-dimensional objects that float in a space of higher dimensions. These branes could collide occasionally, causing the creation of new universes in a cyclical pattern of cosmic birth and death. Their cyclical model of the universe, in which each cycle begins with a big bang and ends in a big crunch, only to begin again, introduces a temporal dimension to the concept of the multiverse, suggesting an eternal sequence of universes, each one emerging from the ashes of the previous one. Another intriguing aspect of what could exist beyond the observable universe is the role of dark matter and dark energy, mysterious components that constitute about 95% of the total mass and energy content of the cosmos. In other parts of the multiverse, the composition and the impact of these dark entities could be quite different, which would give rise to universes that expand and contract according to different rhythms and patterns. As we continue to expand the limits of technology and observation through missions such as the James Webb Space Telescope and observatories like the Event Horizon Telescope, we obtain more tools to know the limits of the known universe and perhaps glimpse the structures that are beyond our perceptive reach. Each new discovery feeds our theories and models, refining our understanding and, at times, tearing down ingrained beliefs about the cosmos. Furthermore, the search for a unified theory of quantum gravity stands as one of the most promising avenues to understand the true nature of the universe, including what lies beyond the observable horizon. This theory aims to reconcile the principles of quantum mechanics that govern the subatomic world with general relativity, the theory describing the gravitational structure of matter. Achieving this reconciliation could someday allow us to understand not only the quantum aspects of the early universe, but also the vast, unobservable regions that lie beyond. Ultimately, our journey to understand the universe reflects our innate desire to explore and comprehend the unknown. It is a journey that takes us not only through the physical expanses of space, but also through the vast landscapes of human imagination and thought as we travel through the cosmos. Each discovery is a reminder of our smallness in the face of the immensity of the universe and a testament to our determination to understand the infinite. This journey, driven by our boundless curiosity, guarantees that, as we look at the stars and reflect on their secrets, the story of our exploration will continue to unfold, always extending towards the end, always receding towards the horizons of our knowledge. The exploration of what lies beyond the limit of our observable universe is not only a scientific endeavor, it is a philosophical and spiritual journey that challenges us to think about our place in a potentially infinite cosmic tapestry. Each theory and each observation brings us closer to understanding not only the universe, but also our relationship with it, a relationship woven through the fabric of space and time, connected by threads of light that unite us to the most distant galaxies, calling us to explore, to understand, and dream.